Good afternoon, everyone. Thank you so much for joining us. My name is Katie Rowley, and I'm with the NOAA Central Library, who is very happy to host our NOAA Innovators Talk today. A few logistics to start out. Everyone who is an attendee is muted on this, so if you do have a question, be it technical or for the presenter, please place that in the question panel, and we will get to those at the end of the presentation. If it is a technical issue, I advise trying to log out and log back in. That fixes most audio or visual issues with GoToWebinar. If you are still having issues, you can always chat me, or you can send an email to library.seminars@noaa.gov. And with that, I'm going to turn it over to Tiffany House for the introduction of the speaker today.
Thanks, Katie. Good afternoon, everyone. I am happy to join you all today, and I hope everyone is staying safe and healthy at home, whether you're at home or in the office. My name is Tiffany House, and I am the NOAA SBIR Commercialization Specialist. My office, the NOAA Technology Partnerships Office, and the NOAA Central Library teamed up to organize this series that features NOAA and SBIR-funded technologies. Arete Associates received a Phase 2 award in FY 2019 from the NOAA SBIR program. It hasn't been that long for them, and yet they are ready to talk to us about their technology, so I'm excited about that. The SBIR program provides competition-based awards to small companies for R&D to transform their innovative ideas into commercial products. All SBIR proposals must directly benefit the NOAA mission and have excellent commercial potential. This technology is available for Phase 3 under the SBIR rules, which means it can be acquired as a sole source procurement for NOAA and other federal agencies. Arete's FogViewer system is an innovative passive sensor suite that aims to provide visibility measurements from a system which is simpler and less expensive to deploy and maintain in port systems. Amanda Steck joined Arete Associates in 2019 and focuses primarily on computer vision and image processing for machine learning applications. Ladies and gentlemen, it is my pleasure to introduce Amanda Steck.
Hello, hello. So yeah, like Tiffany said, my name is Amanda and I am here from Arete Associates. It was a very good attempt at pronouncing the company name, but almost nobody can get it right the first time. So yeah, Arete Associates. I also have in the room with me Tim Klein, who is the principal investigator for FogViewer. He will probably not speak up too much, just if I get stumped by any technical questions at the end. So yeah, we came under Phase 1 funding for FogViewer in July of 2018, and our Phase 2 funding continues through summer of 2021, and our TPOC is Rob Loesch, whose email is on that slide that you should be seeing right now, and he's been great and a great guy to work with and very excited about this project. So we're very excited to be here and present some of our work. So without further ado, let's see if I can, there we go, figure out my slides. All right, so I want to kind of start out with establishing the problems with low visibility situations. We're going to focus a lot on fog, but I'm going to talk about things which are not fog and how you can have a variety of low visibility situations and why we care about them, and then our proposed solution to them. So it really boils down to low visibility conditions cost money and lives, and if that's all you take away from this, these first couple slides, that's really all I need you to take away from it. So I have a couple of sort of, I guess, bigger in the news examples on this slide. So the Port of Galveston is pretty notorious for having heavy fog conditions, and you have a lot of cruise ships that need to get in and out of there, and there can be huge delays in getting ships in and out if it's foggy. And so you kind of need to know, how foggy is it? And that's just a money issue, but you can also cost lives in fog conditions. And so I'm sure we all heard back in January of this year, which I know seems like forever ago right now, but back in January there was the helicopter crash that killed Kobe Bryant, and actually pretty recently they've made some preliminary rulings that this was due to sort of low visibility fog conditions causing the pilot to be disoriented and ultimately crash and kill 9 people. So, you know, it's not a trivial matter to
Amanda, this is Katie, and I'm going to break in really quickly because we are not seeing your slides advancing.
Sorry, I haven't been advancing.
Oh, you haven't been advancing?
Nope.
I'm sorry. I was going to
No
say
worries.
we had okay.
Yep.
I will let you continue then.
So as long as you're seeing slide 2, I'm assuming.
We are not.
No.
We are not seeing slide 2.
This is
if you go to your sharing tab,
oh,
you should.
Yep, that's what I did. Yep, I'm sorry. I knew I was going to have something.
No worries. Okay, we are now seeing slide 2. Thank you.
There we go. Okay. Well, there's the headlines that I was talking about. Sorry about that, guys. I had to minimize my screen earlier so I could, you know, leave the room. Okay, so yeah, so there's my cool headlines that I was talking about. So now let's talk about some other headlines. So this is sort of like the beginning of a movie where a bunch of little news clippings flash through. That's what I was trying to do here. So, right, so those were sort of like big, huge newsworthy events, but this can be sort of, you know, smaller scale as well. So, you know, I found an example in the news about, you know, an intersection in a small town where you can wind up with patches of really dense fog, and it can be really dangerous. But, you know, it's not a huge port. It's not an airport, right? It's a smaller situation, but, you know, you can still have loss of life. You can still have property damage, you know, things like this tractor trailer accident, you know, that happened along a freeway. It's like, you may not always have foggy conditions, but you definitely need to be able to deal with them when you do have them. And to give you guys, you know, some hard numbers, because I'm a scientist, I really like hard numbers. The Federal Highway Administration reported more than 38,000 vehicle crashes and more than 600 deaths due to foggy conditions per year. So that's, you know, a pretty serious problem. I actually didn't know this, but apparently in India, fog, like they have a really bad fog season, which is what this picture in the lower left hand is actually of, and they report more than 12,000 deaths due to fog-related accidents in 2018. So it's a really big problem, and you need to have good reporting of visibility conditions. So then, you know, I've been focusing a lot on fog, but I grew up in the upper Midwest, so I am no stranger to like whiteout blizzard conditions, and that's another situation where you can have low visibility conditions that can change relatively quickly, and you need to have accurate visibility reporting, you know, to protect life and property. So I didn't find any, you know, good news articles about blizzards because, of course, it's the middle of the summer right now. But you know, that's a thing. I also found some very recent news articles about sort of a different kind of visibility problem, which is blowing dust. And this happens a lot in the Midwest, especially if the fields get dry and you get some good winds that whip across those like corn and soy fields. You can wind up with basically whiteout dust conditions. And you know, that can be very dangerous for these highly traveled freeways that stretch across the Midwest. And I found another interesting example, and that's in sort of the top right here. And this is, you know, a collision that you know, killed one and injured 2 because someone was, you know, burning some brush in their field, and the smoke obscured the road, and 2 people, you know, 2 cars collided head on. So, you know, this is a big problem and a small problem, and it's really important that we have good visibility reporting and accurate visibility reporting and timely visibility reporting in a variety of areas. So I've been talking a lot about visibility. I'm sure some of you in the audience probably could, you know, like define visibility in your sleep, but you know, for anyone who maybe needs a good basic working definition, sort of the working definition we're going off of is a measure of the distance at which an object or light can be clearly discerned. And originally, like the original definitions of visibility had a human observer, and they were looking at how well they could, you know, discern a distant object against like a background, usually the sky. And basically the maximum distance they could discern objects was the visibility measurement. Nowadays, most of these measurements are made by sensors, which is what we're going to be talking about today. And I'm going to talk about a variety of ways that these sensors make these observations, and also In the US at least, visibility is frequently reported in miles, so I will be reporting a visibility measurement in miles, but it's really just a distance measurement. And I really liked this image that I was able to find. This was from an article about reduction of like smog and stuff in Los Angeles because of the pandemic, and fewer people are driving and all that kind of stuff. And it's a really like good example of visibility like ranges. You have a very poor visibility condition and then a very good visibility condition with the same objects sort of in view. So yeah, I really like that example, and especially in LA where anyone who's been there knows that the visibility can be horrible there because of smog. So so we've talked a little bit about like what is visibility. And so I want to talk a little bit about like NOAA's needs in particular, because obviously NOAA is the ones who are paying us to develop this. So, we care about what NOAA wants, but these, needs can pretty easily be generalized, and they're somewhat common sense, right? So we need precise and accurate measurements. We need the ability to, put a sensor out in the field and calibrate it out in the field, and then be able to move it somewhere else and recalibrate without completely breaking everything. We need to be able to maintain it pretty easily. We need it to be reliable, right? We don't want to have to maintain it very much, but when we do need to maintain it, it needs to be easy. We want to be able to operate in a variety of environments and weather conditions, right? So from the port of Galveston to, I'm trying to think of a port in Alaska, port of Anchorage, Juneau, somewhere in Alaska, right? We need to be able to cover a huge range of environments and weather. One of the NOAA specific sort of requirements is providing updates every 6 minutes. We want to be able to do all of our processing sort of on board. So, there's no processing required on NOAA's end. We're doing all of that, and we just output a visibility number. And the sensor should also allow for remote troubleshooting. Again, we shouldn't have to maintain it very often, but when we do, it's really great if we can sort of log in remotely and do our work like that. And then sort of the last big requirement is low power, hopefully solar power if we can do that, and also inexpensive. So, like just an easy set of requirements, nothing big here, not a big ask. But we think we're going to be able to do this. And so, thinking a little bit about what are needs of other potential customers, right? Because you always want to think about, commercializing your SBIR product. A lot of other, potential customers have similar needs to NOAA. They need updates at regular intervals. They want it to be easy to maintain and reliable and accurate, all those kinds of things. One of the biggest differences is probably just going to be what sort of system does this sensor need to tie into, which we are trying to sort of future-proof against, in that all of our processing, like I said, is done on board, and we're just basically outputting the visibility measurement as, effectively a text string, which should allow us to tie into a variety of different systems, when that time comes. So I've been talking a lot about FogViewer. How about you guys actually get a chance to meet FogViewer now? I wish I had sort of a more exciting picture to show you of the system, but this really sort of underscores how simple the system is. This is sort of the eyes and the brain of the FogViewer system. Obviously, there are power cords and stuff that make for a very unattractive flat lay, so I didn't put them in this picture. But this is basically it. FogViewer is, low cost passive sensors. So, there's no emissions or anything. It's low power. Right now we just run it off of a wall plug, but, like I said, in the field, obviously we want to be able to run it hopefully off of solar power. It reports accurate visibility calculations, and it automatically provides these on sort of whatever schedule you want. So like I said, we've been working off of this 6-minute schedule, but, it could be sped up or slowed down kind of as needed. It's deployable in remote locations, and you guys are actually going to see some sort of pictures coming up of it deployed in super exotic locations like my front and backyard at my house. So, very exciting so far. And it uses multiple sensing modalities. So we have 2 cameras in there. One is an infrared camera and one is a visible light camera. And the nice thing about combining these modalities is that you don't need to have any sort of calibrated targets in your scene or in your field of view. And I'll talk a little bit about that later, like sort of why you would need those and you know, why it's good that we don't need those. So I apologize in advance. I was told at kind of the last minute that this chart is maybe bad colors for some people, so I apologize if you're one of those people. But you know, hopefully the yeses and nos are good if you fall into that camp. But this is sort of just a really quick look at some, you know, the three main current methods of visibility reporting, and sort of taking from those NOAA criteria, we sort of, you know, condense them into this list of criteria, and we're sort of scoring each one. And you know, hint, hint, FogViewer is going to hit every single one of these as a yes. So you know, little spoiler alert there. But basically, the criteria that we're sort of judging these different systems is it self-calibrating? Is it low cost, low power, low maintenance? Do you need to have any sort of targets? Do you need to have, is it day-night all-weather functional? Is it directional? And can it do image reporting? And some of these are not necessarily bad if it's a no, it's just sort of a way of scoring things. So like the directional category basically means, can you point your sensor, or you know, whatever you're using, we'll call it a sensor, even if it's a human, can you point your sensor in a direction and you get the visibility for that particular direction, which may be an advantage if you only care about visibility in one direction. It may be a disadvantage if you want sort of a general visibility measurement, you know, in 3D space. So, you know, so some of these, you know, it's not necessarily bad if it's a no. Same way with image reporting, if it's a no, it's not necessarily bad, but it does allow for, you know, sort of troubleshooting and some historical record. So we'll kind of, like I said, this chart is meant to be sort of a general overview, but I have slides on each of these different methods. So we'll move on to those. So sort of the most basic method of visibility reporting is the human observer that I kind of talked about earlier. This is what it all boils down to. And basically the way that you use a human observer, I guess, is you train a person to give visibility estimates based on, you know, some set of predetermined criteria. So there is some training that needs to go into this. And this is not necessarily the worst possible system, because human observers gauging visibility for human users, you get some of that subjectivity in visibility reporting that maybe you don't get with a sensor, which can be really good. So the human subjectivity is both an advantage and a drawback with this method, right? You can have different visibility reports from just different humans in the same situation, even if you've trained them properly. Another sort of drawback of a human observer is that you require some sort of target. Again, this is sort of what visibility is defined based on, is how well can you see something at a distance. So if there's nothing to see, your human observer is going to have a big problem with that. And human observers tend to not be as great at night. Again, at night you need to have, you know, lights, like calibrated lights at some distance. So, you know, that's not a great thing. The other real problem with human observers is that humans are, you know, cranky and delicate, and they like to eat and sleep and stuff. So you can't just set a human out and have them be, you know, a 24/7, 365, all different weather conditions sort of visibility sensor. You know, you have to feed them and let them sleep and swap out, you know, observers and stuff like that. So that is definitely sort of a problem, you know, where we would rather have just a set it and forget it sensor, and humans just can't really fill that niche. So then the next method is what I'm calling active scattering. There's a sort of a couple different subcategories of active scattering, but I'm just going to group them together as one. And basically the way these all work is you have some volume of air, and I have this picture here, and hopefully you guys can see my mouse as I'm gesturing around, but you have this volume of air here in between your emitter and your sensor. And I may have those backwards, but for the purposes of right now, we'll say that the left one's the emitter, the right one's the sensor. And so your emitter is going to shine a laser away from, you know, the sensor, right? So it's not shining it at the sensor. So your emitter is shining a laser through the volume of air, and if the air is not clear, some of that light will get scattered. So you'll have light scattering off of this volume, and it will wind up in your sensor. So it's sort of an inverse thing. The more light your sensor sees, the less clear your air is. And so these are not necessarily a bad method for visibility. They can be very accurate, very repeatable. They are not as weather sensitive as, you know, a human would be. Some of the drawbacks of them is that they're not cheap systems, depending on sort of which one you go with. There is some dependency on the relative position at like the relative angle of these two, you know, your emitter and your receiver. If they're not quite calibrated properly or positioned properly, you can have loss of accuracy from that. And so that's not ideal. They also require a heater, which is a big energy hog, as I'm sure you can imagine. And one thing that I would say this is a drawback, it's not necessarily a drawback, but they are not directional. I sort of think of them as a point source measurement. And what I mean by that is basically you only get a measurement of visibility in this chunk of air near your sensor, which, you know, again, if you can assume that your visibility is homogeneous over the region that you're reporting, that's fine. But if it's not, right, if you just happen to have this guy in a clear area and everywhere else is foggy, you're going to get a misleading visibility measurement. So, you know, I think of that point source measurement as a drawback, but, you know, it's not necessarily one. So then our last sort of method that I want to talk a little bit about is not one that's commonly used. There's a lot of research that's gone into this, but not a lot of use necessarily. And that is like other image processing methods, which FogViewer is an image processing method, so that's why I call these other ones. In theory, these can have very good results. You know, academically, they can provide very good visibility measurements, but they tend to be tailored to very particular applications. Frequently, they're only good for daytime. They usually require a lot of knowledge about what you're looking at, right? So you either need to have known targets or known distances within a scene. Like you need to know a lot about what your camera is looking at. They don't necessarily adapt super well to a variety of weather conditions, and they don't guarantee that you can take your setup, move it to a different location, and have it work just as well as it did before. So these tend to be very delicate. They're good in theory, but not as great in practice. So that's just sort of the third sort of method that I wanted to touch on. So then if we bring back our super cool chart, like I hinted to before, you can see that FogViewer manages to hit every single one of these, you know, criteria that we laid out, maybe conveniently because we chose the criteria and we have the system, but, you know, it works. But the nice thing about FogViewer is it is self-calibrating. It's low cost, low power, low maintenance. You don't need any targets in your field of view. You just need to have something there. You know, but you don't need to have anything in particular. It doesn't need to be calibrated targets or anything like that. It works in day and night, which I'll show you in a few slides. It is directional, which, like I said, can be an advantage, can be a drawback. We're considering it an advantage. And it can report imagery. So you can sort of save out this imagery and keep it for some amount of time, you know, for a historical record or sort of for error checking, stuff like that. So let's talk a little bit about our phase one, what we did in phase one. So on the left side there, you have sort of a glamour shot of the phase one system hooked up. This was on the side of our Arlington office, actually looking out over the Reagan National Airport, which was very convenient for us that we happen to be so close to the airport there because we can get the visibility measurements from the airport and use those sort of as, you know, known values for all of our testing. So I put a couple example images from that data collection. So you can see that sort of top row, you have a very clear day and you have infrared on the left column and visible on the right. And I apologize, I will probably go between saying visible and EO. Those are the same thing. I'm sorry for anyone who, you know, that terminology trips up, but yeah, so you have your visible on the right. The middle sort of row is like a, you know, mid visibility day, about 5 mile reported visibility, and then the bottom row is a pretty foggy instance. So you can kind of, you know, just visually see the difference in what those cameras are reporting. And then we can actually show you some results after the imagery went through the algorithms that we developed for phase 1. And so I kind of have the, the big 4 examples. So I have, day, night, and then clear and foggy examples. So I know that this text might be a little bit small to read, so I will sort of talk through it. But on the top left here, we have a clear day, a clear daytime image. So the reported visibility from the airport that day was 10 miles, or for that time, and our predicted visibility was 10 miles, pretty good. Below that, we have a clear night, again, a reported visibility of 10 miles and a predicted visibility of 10 miles. And predicted visibility means coming out of the FogViewer system. And then on the right column, we have a foggy day where the reported visibility from the airport was half a mile, FogViewer predicted half a mile. And then we have a foggy nighttime image where the reported visibility from the airport was 1.25 miles. FogViewer also predicted it to be 1.25 miles. So I know that these seem suspiciously good, right? So I want to show you guys another sort of plot which is maybe not so suspiciously perfect. And this is sort of an overall view of the results from phase 1. And so what we have on the x-axis there, this true visibility is that reported visibility that I was mentioning from the airport. And then the predicted visibility, like I said, is the visibility that the FogViewer system is predicting. So in a perfect world, everything would fall along this diagonal black line, right? You would want your predicted and true visibility to be exactly the same. You will see that we definitely seem to follow that trend, but there are some measurements that are off the line. So it gets away from that suspiciously perfect sort of circumstance. And I will also mention that we are using these reported visibilities from the airport as our truth, but there's no way to actually verify that. Like I said, all of these sensors have some inherent issues with them, and so there could be a bias in either direction between the true visibility and the predicted visibility. So we were very happy that it seems to follow the general trend, and that little discrepancies like that could just be a matter of not being able to verify the data as well as we would have liked. So that's sort of the phase 1, really cool, great results. And then moving into sort of what we've been doing for phase 2. So we have been doing some hardware improvements. We got a better IR camera, which is always super fun. It's always great to be able to increase your resolution. And we've been working on doing some of the real-time acquisition and processing. So like I said, NOAA has this requirement where they need updated visibility measurements every 6 minutes. So what we did in phase 1 was we actually just had the cameras recording video constantly for the length of the test. And then we took still frames from that video to do our visibility estimates based on. Whereas now, we're actually getting into that 6-minute mark where we're saying, okay, every 6 minutes you need to get the cameras fired up, we need to take imagery, we need to process the imagery, and we need to output these visibility measurements, which it turns out, is a non-trivial task, getting hardware to cooperate and communicate with each other properly. We had been planning on this spring taking a field trip out to Virginia Tech, where they have this really cool smart road setup, and you can do very calibrated testing on this smart road, and you can make fog, and you can know exactly how foggy it is and set out targets and everything. So that was supposed to be happening in early May of this year, and then the world started ending and COVID happened, so we weren't able to go do that testing. So we've been doing all of our testing in our office in Huntsville, Alabama, and it's actually been going really well. The nice thing is that here we can sort of do a little bit of testing and reevaluate and fix some problems, and then do a little bit more testing, and so any problems that we have don't persist long enough to screw everything up. And we have a longer field test planned for late 2020, so hopefully in November or December in Santa Barbara, where we're going to basically take the system, drop it off on the roof of a building and say goodbye, and let it run for a while on its own, and see how it does. Really sort of simulate that extended maritime deployment. And I put a couple of glamour shots on this slide, just from some of our phase 2 testing. These were both taken over the weekend of the 4th of July. So the bottom one you can see was my neighbors. This is out the view of my front door, basically. So my neighbors setting off some fireworks in their driveway, which was kind of fun to catch. And then the top one was, I think, the next morning, and for some reason there was a party of crows, on our driveway, plotting things probably, but that was a kind of a fun little Easter egg to find when I went through the imagery when I brought it back into the office. And these images are a little bit fuzzy. There was an issue with the focusing on the camera. So yes, they are fuzzy. It's not you. That's another little bug, that gets squashed along the way. So we've been doing all this testing. We have some very sort of preliminary results to be able to report. And basically what we did for these is we, took some of the imagery that we were taking during our testing, and we, cropped it so that it is in the same sort of size and format and everything that our phase 1 imagery was in. And we just stuck it in the phase 1 algorithms. We didn't bother to recalibrate the algorithms or anything like that. We just fed it some imagery and wanted to see what it would put out. So on the left-hand side there, you have a pair of images, and these are, rather than out my front door, these are out the back side of my house, looking out onto a swamp that I live on. And so, that was a clear evening. You can see that the reported visibility, again, taken from the Huntsville airport, was 10 miles, and the predicted visibility for this set of pictures was 8.2 miles. And then we have sort of a similar pair of pictures over on the right here. These are from downtown Huntsville. So this is the view off of the parking garage of our office here. And again, it was a fairly clear day. So we have a reported visibility of 10 miles and a predicted visibility of 8.3 miles. So, it'd be better if the numbers were spot on, but the fact that they are at least relatively close and believable numbers without any sort of recalibration or anything like that is a very good result for us, and we're very excited about seeing that sort of stuff. And it definitely means that with a little bit more work, the system should be able to be picked up and taken somewhere else, and it should be giving good visibility measurements with very little sort of prep time. So that's sort of where we stand right now. Sort of where do we go from here? By the end of phase 2, we plan to have a fully deployable prototype. And by that, I mean we have something in a case that we could send to one of our other offices, and they take it out and set it up, and it just works right out of the box. So that's obviously a good goal to have by the end of our phase 2. And once we hit that, we should also be able to produce sort of a limited run of additional FogViewer units, sort of in-house. Eventually, we would want to sort of, really make it sleek and smooth, and miniaturize everything, and sort of start to, get some of the things sort of combined and all that kind of stuff. So eventually, it would be, a really nice, like, pretty looking product. And so, while obviously FogViewer is really influenced by the needs of NOAA and, sort of maritime environments, like I sort of said at the very beginning, the low visibility situations and places where you need visibility measurements are all over the place, right? So you have things like autonomous vehicles, you have offshore like oil rigs, you have ports, obviously, but you also have the ships that are coming in and out of ports. Maybe it'd be great to put one of these on a cruise ship or something like that. You have airports, you have Department of Transportation, put it along freeways. You have areas which are influenced by like wildfires, stuff like that. So there is almost no end to sort of the situations where a product like FogViewer could be useful in being able to give, real-time, on-location visibility measurements to areas that need it. So that's sort of most of the technical stuff. I kind of saved all of the, more boring stuff I felt like till the end, except for the team. The team is not boring, but all that other kind of stuff. So I want to really quick give kudos to everyone that's on the team. And this is combined phase 1 and phase 2. So there's a lot of people on this slide, but some people have sort of come and gone. So We have Steve Anderson. He's, you know, sort of our maritime guy. He knows all of this kind of stuff, and he's just like wicked smart with that kind of stuff. We have Katya. She does a lot of the mechanical engineering. She makes sure that, you know, when I take the system from place to place, it doesn't fall apart. We have Nate. He's one of our interns here in Huntsville this summer. He's been doing a lot of work on sort of hardware integration and making sure that what we have will actually talk to NOAA systems, and, you know, that we're not just shouting into the wind. We have Tim, who's the PI. He's sort of the glue that holds everything together between phase 1 and phase 2, and always full of questionable ideas, but we're going to say good ideas because he's sitting in the room with me. We have Bree, who's another one of our interns here in Huntsville. She's been doing a lot of algorithm development for us. We have Retha. She's sort of our atmospheric expert. We have PJ, who does a lot of the sensor work. He was really super important for phase 1, and he's kind of dropped off a little bit in phase 2, but like he's the guy we always go to when we're like, oh, how did this work before? He's the guy. We have Sam, who's been doing a lot of the algorithm development as well. And then there's me, who's been sort of just making sure that all the pieces wind up where they need to be and that everyone is, you know, getting work done. So that's sort of the team. A little bit about the company. So I'm never good at doing this sort of pitch for the company, but I will do my best. So Arete, basically, we are a company of smart people, lots of scientists and mathematicians and engineers. We're about 300 people in a bunch of different offices, and we really have smart people looking to solve hard problems. And we sort of specialize in low signal and high noise environment sort of situations. And it's just been, it's a great company. I think I can say that somewhat honestly, since, you know, I'm not a lifer. I've only been here for a year and a half. So it's a great company to, you know, work for, and a great company to work with. So yeah, cool stuff. And then, like I said, we have a bunch of different offices. I thought I'd put up a map just, you know, in case anyone's curious. So I am currently in our Huntsville, Alabama office, which is this guy right here. We also have offices in Florida. We have 2 offices in the DC area. We have offices in Arizona and Colorado, and then our headquarters are in Los Angeles. So we're very diverse, and it's actually been sort of an advantage as, you know, the whole pandemic thing hit, because we were already used to calling each other on Skype and stuff. So there was very little learning curve sort of as we had to deal with working remotely. So that's been a plus, I guess. But yeah, I think that's actually basically it. This is my thank you slide. So thank you to everyone for, you know, listening in and giving me some time today. Thank you, NOAA, for giving me this opportunity to be able to present our work and, you know, get other people as excited about it, hopefully, as we are. And, you know, I know we have some time now for questions, or if you have any other questions, you can feel free to email myself or Tim, or, you know, you could probably get a hold of Rob and he could forward questions to us. I will mention that any questions that are like super like secret sauce kind of stuff, it's not that we aren't unwilling to talk about them, but I definitely won't be able to answer them now. But definitely get a hold of us if you have questions that are like more specific than what can sort of be answered in a public forum. But yeah, that's FogViewer.
Thank you so much, Amanda. This is Katie Rowley from the library, and we're going to be going through the questions that have been submitted. So if you do have a question, you haven't submitted that yet, please enter that into the chat panel, or the question panel, excuse me, and I will be asking those. Okay, so I'm going to pick off the first couple questions we have right now. This, Amanda, may fall into the secret sauce kind of area, but I'm gonna take a stab and see if you can answer this. Can you provide a high-level explanation of how the sensors work? What's the methodology, algorithm behind the visibility detection?
I mean, yeah, I can provide a very high level, but yeah, if whoever asked this is unsatisfied, feel free to follow up with us. But basically, you know, the sensor is cameras and then a computer. So we have our two cameras, the IR and the visible camera, and they're literally just cameras. Like there's nothing super special about them. They take the imagery, and then we have a certain amount of sort of pre-processing, and then I guess really the secret sauce is in the algorithms that we use. And so, the imagery feeds into there, and it does, the stuff that it does, and then it outputs a visibility measurement. So my guess is that would be an unsatisfactory answer. So for whoever asked that, do please follow up with us.
I'll say like one more sentence on it. So this is Tim. So we go on, so since we have multiple sensing modalities, the IR and the visible, and they each react differently to fog, as you saw in the picture. So that's why we don't need a calibrated target, is because we basically have two different looks and at two different visible and infrared wave bands. And based on the way those two interact with the environment around it, then we can extract the visibility out.
See, that's why Tim's here. This is great.
Thank you so much for that answer. Okay, next question. Being passive, is it true that it will not work very well under really dark conditions?
So this sort of gets into the whole, there needs to be something for it to see, right? You could definitely have one of the active scattering sort of sensors, and you can have that in the middle of a very dark field, and you don't need to have any light or anything like that, and it will be able to give you visibility measurements just as good as during the day. So our system probably would not be able to do that, right? It needs to have something to look at. But again, because we're combining infrared and visible, there's usually something to look at in one of those bands. So that's an advantage of having those two different sensing modalities. But also this starts to get into sort of an issue of, who are you providing visibility measurements for, right? We're providing visibility measurements for people. And so if it's so dark that nothing is visible and there's nothing to sort of latch onto to see, that may also be a scenario where people also can't navigate. So it is, maybe not as good as, some of the other methods, but it does help to bring in that little bit of subjective, human experience as well, in terms of like, well, could a human actually navigate through this situation or not?
And since the infrared is a thermal band, so the infrared will have as dark as it can be, as long as there's thermal imagery. Obviously the visible is, like your human eye.
Yeah, so if you're on the moon or something and it's very dark, you might have a hard time.
Understandable. Okay, our next question. Do you have plans for testing in more extreme environments after the Santa Barbara test, et cetera? I mean, for example, freezing temperatures, snow, ice, freezing fog.
We don't have any specific plans, but we definitely would like to. We're taking it out to Santa Barbara because that's sort of a nice controlled place where we know that it can sort of hang out and be safe. But I have thought about, taking it back home to Minnesota at some point during the winter and seeing how it does. It's just sort of a matter of making sure that we have somewhere that we can put it, and also being able to travel again. That would also be super nice.
So we had an existing relationship with the folks at Santa Barbara, so that made the decision to do the testing there really easy. I mean, obviously we want to go in a more extreme or more varied environment. But.
Yeah.
Great, thank you. We have another question on the images. How are the two images used together?
So that starts to get into sort of some of the secret sauce stuff again. So we have these two images returned by our cameras, the visible and the infrared. And basically our algorithm is designed to be able to suck in those images with a little bit of pre-processing done. But basically the algorithm is designed to suck in those images, and that's kind of where the magic happens in terms of like, how does it sort of combine those images and use them to be able to extract the most meaningful information from both and be able to return that visibility measurement. So it's another one where we would love to talk more about it offline.
Thank you. Okay. Next question. How long or how much training data is required for sensor calibration? Can you describe the calibration process a bit more?
I mean, that is one of the million-dollar questions. It's not so much like how long, it's really about getting a good variety of data. And that's something that we've been, would have been really great if we could have actually made it out to Virginia Tech, was because we could have gotten a lot of data at a variety of visibility levels. And it's definitely something that's a little bit tougher now that we're sort of just at the whims of the weather. But what you really need is you need a good variety of data. Like, it doesn't help to have a whole bunch of 10-mile visibility data and a whole bunch of 1-mile visibility data, because then you will never be able to accurately predict in between. And so really it's a matter of having a good sort of catalog of all visibility measurements. And so that's sort of a process that we're working through right now, is like, how much data do you really need, assuming that you have a good variety of it? And how much do you need additional then when you take your sensor somewhere new and you need to do that calibration? How much do we actually need? Like, do we need a little bit? Do we need a day? Do we need a week? Do we need a month? Like, that's really sort of the question. And a lot of it, again, depends on how quickly does the weather change? Like, how quickly can we get that good variety of data when we take it to a new location?
For phase one, we were able to train it within a couple of weeks of data. Yeah. So, but that was a specific location in a specific environment. So yeah, depending on a new environment, it might change.
Thank you. Our next question, can you give an idea of power consumption for continuous use?
That's another thing that we're sort of working on as part of our phase 2 stuff, is, because like I said before, we weren't sort of having it run like it would in real life. So that's a good question, is what I would have said when I was in grad school. Because we know that it will be duty cycling, right? It's not going to be running all the time, but it's just a matter of sort of how long does it take everything to run once we sort of have all the processing going and all that kind of stuff. And, do we need to do active cooling and stuff like that, which we don't think we should have to do. So, it's a...
I mean, and to get a little more detailed, there's basically 3 components. There's the cameras, the computation, and then the housing. Each one has a power draw. And the cameras are like tens of watts. The computation, you can get very capable low power computation, and that's the duty cycle. So you're talking tens of watts there, and then the housing is the big question of how much you need to go in there. So probably 100 watts or so would be ballpark, but that's one of the things we're trying to figure out.
Thank you. Our next question, what's an estimate for the final package, what the final package may cost? Is it, $10, $100, $1,000?
So that one, it really depends on, the driver is the infrared camera. So how well you need the infrared camera to work. So we upgraded the camera during phase 2 to so we would get a better resolution. It's unclear whether we needed that or not, but when you're collecting data, you can always go down in quality. You can't really go up. So the current, so that's the big driver. The rest of the housing and the embedded computer, basically COT stuff, they're fairly inexpensive, but it's probably it's 4 digits, but that how well it actually where in that it's going to fall, it depends a lot on your sensor selection.
And obviously there's a sense of scale as well, yeah. Right? When we're making one system, it's obviously more expensive than if we could go into full production and make 100 systems. So there's that too.
Okay, thank you. We do have 2 kind of separate questions on a similar topic. does the system require a fixed target, or would something like the horizon, a kind of non-directional visibility, work?
So it doesn't require a fixed target. So there is no requirement that like you need to have, you know, stationary things in your scene. So which is why, you know, it's important if we want to put it into like a port or an airport or something where there's going to be things moving, right? You need to be able to sort of handle things moving from image to image. But it does require something. So if you're just sort of staring off at the horizon across a cornfield and nothing else is in your image, it may not be ideal, right? Because again, you don't have anything to sort of gauge on. We've talked a little bit about like if you're looking out at the open ocean, like that's different because now you have waves and things like that. But it doesn't require like a fixed known target. It just requires that there be something that you can look at and, you know, sort of gauge visibility based on that. And obviously you don't want your entire scene to be moving between each image, but like if you have, you know, boats or cars or trucks or something moving, you know, every 6 minutes or something, little things are fine. And, you know, changing, you know, building scapes over time will be fine, but there needs to just be something to look at.
Great, thank you. Okay, we've got about 10 minutes left in the hour and several questions, so I'll try to get through as many as possible. Tiffany, did you want to ask your question?
Can you hear me?
Yes, go ahead, Tiffany.
Oh, sure. I have a long one. It's okay if you wanted to get to the other questions before me. What do you think?
Well, we did have a similar question to what you asked about. So I will ask a part of your question, Tiffany. What are the dimensions now, and how small do you want it? Will the miniature size be solar powered?
Yes, if you guys don't mind, I can actually go back to sort of our picture of the system. Let's see if I can do that fairly quickly. Okay, so right, so I had this picture of the system, and I know that this picture doesn't have a great sense of scale to it. So to sort of give a sense of scale, this box is maybe about, I don't know, like 9 or 10 inches sort of along the short side, and you know, somewhere between 12 and 15 inches on the long side.
It's a 9 by 14.
Yeah, like 9 by 14, and it's about, I don't know, 5 to 6 inches sort of tall, which of course you don't get because it's laying flat on the table. And that box is not full right now. It's sort of just an off-the-shelf case that we got that happens to fit the stuff that we need in it. So that box could definitely be smaller, although we ideally would like to package some of these sort of like power cords and stuff actually inside that box. So that box is a pretty good representation of how big sort of what I keep calling the brains of the operation. That's kind of about the size that it will be. And obviously like that box could be mounted on a pole or something like that. Like it doesn't have to necessarily be in a particular orientation. And then, you know, sort of knowing the size of that box, this camera housing again is, you know, sort of about a foot long and sort of about, I don't know, like a 4 to 5 inches, you know, wide and deep kind of. And that's what houses our 2 cameras. And then again, that can also be mounted sort of on a pole or, you know, on a building or something like that. In terms of how much smaller it would eventually get, it really depends on how intense we want to go with sort of manufacturing. So if we want to continue to sort of do like limited run, off the shelf COTS kind of stuff, it probably won't get a ton smaller, but if we sort of wanted to get, you know, custom, you know, brain filling basically made to go in that box, we could definitely reduce the size, but probably not by more than maybe like 25%. You know, it still needs to have some amount of sort of dimension to it.
Thank you. I want to grab a few more questions here, and if I don't get to all of them, I will pass them on to you to answer offline. So our next question is, how do you keep the housing windows clear or clean so it does not bias your measurements?
So that's something we thankfully haven't had to deal with too much yet. So I guess it's fortuitous that I'm on this slide. We actually do have sort of a little hat that sort of shields the front of our system. So far right now, and I've had this system sitting out in the rain at my house, and it has never gotten so gummed up that it hasn't been able to at least take imagery. Whether, how you sort of process that imagery is another question, but you obviously want it to be able to handle that, right? You don't want to have to send some guy up on a ladder every time it gets a little bit of water on it to, wipe off the water. So eventually we may need to put some sort of automated little, tiny windshield wipers on it if it was in a really bad environment. But our goal is to have it be able to function pretty well even as the windows get sort of grimy with, every so often someone's going to have to go out and, maybe wipe them down. And then also the goal is to be able to have it self-report once the windows get too dirty, right? So it could say like, oh, my windows got covered in mud or dust or something. I need someone to come out and clean me. So that you don't have to do it if you don't need to.
Yeah, and then so since that's always going to be part of the image and happen generally slowly, so some of the pre-processing can take out if there's some sort of film or degradation on the window.
Understandable. One of our attendees is saying that in a marine environment, sea salt might be an issue then.
Yeah, and that's definitely why we wanted to be able to sort of self-report, like, hey, I'm gross, please come clean me.
Understandable. Okay, Tiffany, you're gonna finish up your question there.
Yes, I wanted to say that great minds think alike, because that question about the size was one of my exact same questions, but I also wanted to know, with the smaller size, would that still be solar powered? I know you said you were working on that as an option.
I mean, I don't see why not. Like the advantage, so if we were to move to sort of a smaller size, the assumption would be that we would be making it more efficient in terms of its power consumption. And so that would hopefully make it easier to run, sort of on a limited power budget. So it certainly wouldn't make it worse, and it would hopefully make it better if we could compactify things and get rid of, maybe some things that are in the COTS stuff that we don't actually need. That should hopefully improve the power budget rather than make it worse.
And even now, I mean, it depends a lot on the duty cycle, but once every 6 minutes, I mean, I think we're in the range right now where we could run on solar with the current prototype.
Okay, and I also wanted to ask, you said that this will be ready by the end of phase 2, I think you said. And if that's the case, can you just give people on the line who doesn't know what the end of phase 2 mean? Can you just give them an estimated time frame?
Oh yeah, sorry. That should be the end of next summer, I believe, is sort of when we end our development, sort of phase of phase 2. So by about this time next year, we would have hopefully a working prototype that you could, stick in a Pelican case and take out and set up, and it would just work. Something that we could, sell you basically.
Yeah. So for now, we have this system. We're going to do the testing in Santa Barbara and probably one iteration of changes in the winter and spring of next year. But yeah, so generally that's the plan, is to have something that could be made available about this time next year, maybe next spring.
Yeah.
It depends on what your actual application are and what your needs are. So that, I mean, it could be earlier depending on what people wanted.
Great, thank you. I'm going to grab one more question. We do have several that we won't be able to get to, but one last question, hopefully an easy one. If someone accidentally moved one of the cameras a little bit, is the measurement still accurate, or does it need to be recalibrated?
It should be okay. So thankfully, both of the cameras are mounted in the same housing. So you don't need to worry about one camera getting offset from the other. If let's say this entire head assembly got, bumped, if it was bumped a little bit and it was still looking at most of what it was looking at before, should be fine. Like the algorithms should be able to handle that just fine. If it got turned 90 degrees, you might need to recalibrate or send someone up to sort of put it back. But the nice thing is you could just sort of put it back to where you thought it was. And again, it should be fine as long as it's relatively close.
Yeah, like when you've been taking data, you haven't been.
No, I've been just setting it on my front porch.
Great, thank you so much. Well, we are run up to our 1 o'clock hour, so I am going to grab all of these questions that we did not get answered and pass them on to you to answer offline. And with
Awesome.
that,
Thank you so much.
yes, I would like to thank everyone for joining us today. Thank you for presenting, Amanda and Tim and Tiffany, for bringing them in for the NOAA Innovators Series. This has been recorded, so if you missed it or if you wanted to pass it on to a colleague, we'll be having it up on our YouTube channel shortly, and that is youtube.com/NOAA Central Library. And with that, I hope everyone has a wonderful and safe rest of their Wednesday. Thank you, everyone.
Thank you.
Thanks.